what if you could?
Right.
What if stacking enough perfectly round objects in exactly the right way and spinning them at exactly the right speeds could somehow actually forge a hard, sharp 90-degree angle?
It sounds like a total visual paradox, honestly.
Oh, man.
But that is exactly the mathematical reality we are unpacking today.
Yeah, it really is.
It's this fundamental truth that underlies geometry, signals processing, and even audio engineering.
So today we are taking a deep dive into a really fascinating visual breakdown called the sound of a square wave.
Which is such a cool source to work with.
It is, because it's uniquely this entirely silent animation,
Mm-hmm.
but it implies sound by translating the invisible world of harmonic frequencies into visible rotating geometry.
Yeah, it's literally mapping out time, visual movements, and implied frequencies frame by frame.
Right, and our mission today is to understand how simple, smooth curves can be stacked together to build these really sharp, rigid shapes. So, okay, let's unpack this.
Let's do it.
Because to understand how a complex, jagged square wave is built, we first have to establish the foundational building block, right?
Right. You can't build the wall without laying down that first bowling ball.
Exactly. So in the visualization, the very first 3 seconds start with this single, smooth red row. And it's labeled n equals 1.
Right. And what we are seeing there visually is just a single rotating circle.
Right.
Geometrically, it's known as an epicycle.
An epicycle? Okay.
Yeah. And imagine a single point on the outer edge of that spinning circle. As time moves forward, if you were to just trace the vertical position of that point, it draws this perfectly smooth, gently rolling sine wave.
Just totally continuous.
Exactly. It is the visual equivalent of a pure, clean tone. There are no sharp edges, just a continuous flowing curve.
It's kind of like drawing a perfect continuous loop with a pen without ever lifting it off the paper. It's just effortless.
That's a great way to picture it, yeah.
And mathematically, this single red sine wave represents what the source calls the fundamental frequency. They map this out as the drawl.
Right. The root.
Yeah, the baseline. Like if you were playing a note on an analog synthesizer, this is the core pitch you are hearing before any texture or buzz or distortion is added to it.
Just the pure tone.
Right.
Yeah.
But I have to ask, looking at that smooth red sine wave, there is absolutely zero hint of a square in it. So what does it actually mean that this smooth line is the fundamental for building something that, eventually has sharp corners?
Well, because the fundamental frequency, that $, it dictates the overall width and timing of the shape. It sets the mathematical boundaries.
Okay, so it's like the footprint.
Exactly. Think of it as the outer perimeter of our construction site. It tells the system exactly how long the final square wave is going to hold its high plateau before it drops down to its low plateau.
Oh, I see.
Yeah, and it sets exactly what the overarching period of the wave is. So the red wave provides the blueprint for the timing.
But it still totally lacks the shape.
Right, it completely lacks the shape. So to get the shape to turn that rolling continuous hill into a steep cliff, we have to introduce complexity. We have to basically start roughing it up.
Which brings us right to the next phase of the animation. Once we establish that smooth baseline, the math kind of demands we introduce more variables to flatten the roof, right?
Yeah, the second row comes in.
Right, between 3 and 7.5 seconds, a second row is added. Visually, it's yellow, and it's labeled n equals 5. And immediately, that perfect pure wave starts to deform.
It completely loses its purity, mathematically speaking.
Exactly. The top of the continuous curve starts to flatten out into a plateau, and you begin to see these visible ripples appearing across the surface.
It starts looking a lot more square-like.
It does. And then shortly after, a third variable joins the mix. This is a blue row from about 7.5 to 16 seconds labeled n equals 9.
And that's where the shape gets even sharper.
Yeah, the plateaus on the top and the bottom get significantly flatter. The drop-offs at the sides get much steeper, and those ripples get way tighter and more compressed at the edges.
So let's break down the actual implied frequencies being injected here, because this is pure Fourier series mathematics in action.
Okay, lay the math on me.
So when we introduce that yellow n equals 5 row, we are adding odd harmonics up to the fifth. So our frequency set is no longer just $.
Right.
It has become a stacked summation. So it's $3 plus $3 plus $5.
Oh, wow. So visually, we are literally attaching 3 distinct rotating circles to each other.
Yeah, chain link style.
Like the center of the second circle is pinned to the edge of the first, and the center of the third is pinned to the edge of the second.
Precisely. It's really like the old Ptolemaic model of the solar system, right?
Yeah.
with, planets orbiting on invisible wheels attached to other
Oh,
wheels.
that's a perfect analogy.
And then the blue n equals 9 row pushes it even further. It adds odd harmonics up to the ninth. So our mathematical stack is now Thavo, $3, $5, $7, and $9 and $900.
That is a lot of circles.
Yeah, we have 5 rotating circles, all spinning at different specific odd-numbered speeds, and they're all linked together in a chain.
Okay, but I have to push back here because this brings us to the paradox we started with.
Yeah.
We are adding more rotating circles, right?
Right.
We are injecting vastly more sweeping curves into the system.
Yeah.
And yet the resulting waveform has flatter lines on top and steeper, straighter edges on the sides.
It's totally counterintuitive.
It really is.
Yeah.
How does stacking a bunch of rounded, wavy frequencies somehow cancel out the curves to literally forge a straight line?
Well, what's fascinating here is how the source document visually proves this counterintuitive mathematical reality through the square wave Fourier series formula.
How so?
It all comes down to phase alignment and interference. When we stack these odd harmonics, the 3/4 dollars, the $5, the $7, we aren't just, throwing curves into a blender randomly.
Right, because they are very specific multiples.
Exactly. Because they are specifically odd multiples of the fundamental, their peaks and zero crossings align in highly specific, rigid ways.
Oh, right, because if we were adding even harmonics like $200 or $4 it would just break the symmetry, wouldn't it?
They would.
It would push the wave to one side and give us something like a sawtooth wave instead of a square.
Exactly. Odd harmonics preserve what we call half-wave symmetry, which is an absolute requirement for a square wave.
Okay, that makes sense.
Now think about pure destructive interference. Right at the very top of our original smooth red wave, like the absolute peak of the fundamental, these smaller, faster, odd harmonics are mathematically dipping down.
Wait, really?
Yeah. Their valleys are aligning perfectly with the fundamental's peak.
Oh, wow. So they are actively subtracting amplitude right where the fundamental is trying to be at its absolute tallest.
Exactly.
They are literally squashing the peak flat.
Yes, they are mathematically carving the peak down through destructive interference. And at the exact same time, look at the sides of the wave where the fundamental is trying to, slope down gently to cross the zero line.
Right.
In those exact locations, these smaller, faster waves are pushing up. They are constructively interfering, adding amplitude, forcing that gentle slope to become a steep, nearly vertical wall.
That is wild. So the small, incredibly fast circles act almost like a high-speed mathematical chisel.
That's exactly what they are.
They just chip away the rounded top and fill in the sloping sides to create a rigid box. And I guess the more odd harmonics you add, the finer and sharper your chisel becomes.
Absolutely. And that pursuit of a sharper chisel is what drives us to push these frequencies to their absolute limits in the animation.
Right, because we want maximum sharpness.
Exactly. We have the rough, blocky framework of a square wave from our n equals 5 and n equals 9 stacks. But a true square wave has razor-sharp transitions. To get that, we have to bring in the high-frequency detail.
Which brings us to the most, frankly, chaotic part of the visualization. Between 16 and 17.5 seconds, the green row activates, and it's labeled n equals 15.
And you can see the visual impact immediately.
You really can. The corners of the wave become much steeper, and the overall shape just gets this sudden burst of high-frequency definition.
Right.
And then we hit the grand finale. The purple row activates, labeled n equals 21. Now, all 5 rows, red, yellow, blue, green, and purple, are running simultaneously.
It's an absolute engine of geometry at that point.
It is.
Let's quantify that final stack because the computation happening there is staggering.
Okay, yeah, let's break it down.
So the green row means we have stacked every odd harmonic up to the 15th. And
Yeah.
then the purple row takes it all the way up to the 21st harmonic.
So that's 3 runs, 3 fronts, 5 onic, all the way up through 21 purple. That is a massive synchronized chain of epicycles. I mean, the smaller circles at the very end of the chain must be spinning furiously fast compared to the slow, steady red circle at the base.
Oh, they are.
And all of that chaotic high-speed rotation is what finally forces those vertical walls to stand straight up and that horizontal plateau to lay incredibly flat.
It is, but as you force a continuous function to behave like a discontinuous one, which is, exactly what a square wave's instant vertical jump is, you encounter a very specific limitation.
And here's where it gets really interesting. Because we've stacked 21 odd harmonics to forge this shape, we've used our absolutely finest mathematical chisels.
Right.
And yet precisely where the wave is at its sharpest,
Yeah.
right at that 90-degree corner where the steep vertical wall meets the flat horizontal plateau,
Mm-hmm.
we don't get a perfect, clean point.
No, we don't.
The source specifically points out these Gibbs-style ripples at transitions, these extremely fine, tight, vibrating ripples localized right at the edge.
Yeah, that is known as the Gibbs phenomenon. It's actually named after the American physicist Josiah Willard Gibbs, who mathematically described it back in the late 19th century.
Okay, but why does maximizing the sharpness inherently create this localized chaos right at the edge? Like, if we are adding higher and higher frequencies to perfect the square, shouldn't the edge get cleaner?
You would think so, but you have to remember what we are actually demanding of these continuous flowing sine waves.
Okay.
We are asking a series of smooth rotating circles to instantly start going straight up and instantaneously start going perfectly sideways.
Oh, I see.
We're literally asking a continuous curve to execute a discontinuous right angle.
Which continuous functions fundamentally cannot do, right? They have to flow through the transition.
Exactly. Continuous waves just hate instantaneous changes. So when you stack all these high frequencies to force that sharp corner, you get an overshoot.
An overshoot.
Yeah. The combined amplitude of the waves physically shoots past the target flat line, dips back down, overcorrects, and then finally dampens out into the flat plateau.
It's kind of like the transient response in an electrical circuit, right?
Oh yeah, that's a perfect comparison.
Like if you throw a sudden surge of voltage at a system, it doesn't just instantly sit perfectly at the new level. It spikes, it rings for a millisecond, and then it finally settles.
That is a perfect analogy. That ringing or that overshoot is the Gibbs phenomenon.
Wow.
And what the purple n equals 21 row shows us is that as you add higher and higher frequencies to your Fourier series, you don't actually eliminate that overshoot.
You don't.
No, you just compress it. You squeeze the ringing into a much tighter, faster physical space closer to the edge, which makes the rest of the square wave look incredibly sharp. But the ripple itself refuses to vanish.
Wow. So what does this all mean?
That's the big question.
Right, because we've gone from a single slow-moving red circle drawing a rolling sine wave, and we built it up into this chaotic purple engine of 21-odd harmonics, furiously vibrating just to hold up a square wall.
Yeah, it's a lot of work for a simple shape.
Exactly. So why does this exact mathematical breakdown matter to you listening to this right now? For me, this is way less about audio engineering and more about how we deconstruct incredibly intimidating systems.
I agree completely. If we connect this to the bigger picture, it really changes how you look at monolithic complexity.
Right, because a square wave with its severe, rigid shape, it feels impenetrable. It looks like an absolute.
Definitely.
And if you are trying to learn, say, a new coding architecture or understand a dense, multifaceted engineering problem, it often looks like a square wave.
Yeah.
It seems harsh, abrupt, and just impossible to break down.
It's overwhelming.
But this entire concept proves that it isn't. The rigidity is an illusion created by the sum of its parts. It is actually just a massive, orderly stack of simple, smooth, easy-to-understand components.
And that right there is the absolute brilliance of Fourier analysis.
Yeah.
Yeah, and it's why it is used in everything from, JPEG image compression to quantum mechanics.
Oh, wow. I didn't realize it was that universal.
Oh, it's everywhere. It teaches us that any complex periodic signal, no matter how jagged or noisy or sharp, can be perfectly deconstructed into a set of simple fundamental sine waves.
That's amazing.
You don't have to tackle the jagged cliff all at once. You just find the n equals 1. You isolate that fundamental $1.
Find the first bowling ball.
Exactly. Once you understand the underlying blueprint, you just identify the odd harmonics one by one. You stack the simple curves until the complex reality finally makes sense.
It's profoundly empowering when you think about it. You're literally watching the invisible rules of the universe being drawn out in front of you.
You really are.
So, to summarize the journey we've been on today, we started with the smooth foundation, the n equals 1 sine wave.
The red row.
Right. And from there, we methodically added odd harmonic frequencies because their specific phase alignments were mathematically required to squash the peaks and steepen the sides.
Using that Fourier series formula?
Yes. We watched the n equals 5 row rough up the wave. We saw the n equals 9 row force the walls steeper. We pushed the limits with the n equals 15 row, introducing high-frequency detail.
All those tight ripples.
Exactly. And finally, we arrived at the purple n equals 21 row, stacking every odd harmonic up to the 21st to gradually forge the steep edges and flat plateaus of our square waves, relying entirely on the destructive and constructive interference.
It's quite a journey. And, next time you encounter a complex system that seems impossible to crack, remember that beneath that hard exterior, there is a massive stack of simpler components working together.
You just have to reverse engineer the stack.
Right. But looking back at the Gibbs phenomenon we discussed earlier, this actually raises an important question, one that the visualization kind of pushes us right to the edge of.
Oh, let's hear it.
Well, we saw that adding more odd frequencies made the wave vastly sharper. The n equals 21 wave was far more square than the n equals 5 wave. But we also established that pushing those high frequencies simply compressed the Gibbs-style ripples, right? It didn't actually remove them.
Right, the ringing at the transition was still there. It was just squeezed much tighter against the vertical wall.
Because continuous curves will always struggle to turn a 90-degree corner instantly.
Right, they overshoot.
Exactly. So here's a final puzzle for you to ponder long after we wrap up today.
I love a good puzzle.
If you didn't stop at n equals 21, if you had infinite computational power and you just kept adding odd frequencies into infinity, n equals 1 million, n equals 1 billion, endlessly stacking smaller and faster spinning epicycles, would those Gibbs-style ripples ever truly vanish?
Oh, man.
Would the infinite limit eventually create a mathematically flawless, perfectly flat square wave? Or, because we are using endless curves to try and build a sharp corner, will there always be an infinitely tiny ripple, an endless microscopic vibration hiding at the absolute edge of perfection?
Wow. That is the kind of mathematical mystery that just stays with you. The idea that no matter how much you stack, the curve might never truly surrender to the straight line.
It's a fun one to think about.
It really is. It's a brilliant thought to leave you with. Keep looking for those fundamental frequencies out there, and we will catch you on the next deep dive.